Okay, this is called integration by parts because we're going to break up the integral into two different parts. And it's particularly useful for integrands, and integrand is just what you're integrating, involving a product of an algebraic and a transcendental function. Well, an algebraic function is like a polynomial that you're used to seeing. A transcendental function is anything like the natural log of x or e to the x or a trig function, something like that, something that's not really a polynomial function. So, and it's the product of those two. So x times ln x is a good thing to use here. X squared times e to the x and e to the x times sine x are all good ones here. Integration by parts formula is derived from using the product rule of taking the derivative of a product. So to refresh you, when we take the derivative of a product, remember that we take the derivative of the first one times the second one plus the first times the derivative of the second. Okay, now we're going to turn right back around and we're going to integrate both sides of that equation because whatever you do to one side, you can do to the other. So I'm going to integrate. Basically, I'm just going over here and I'm going to integrate both sides. And if I took the derivative of this, or if I want to integrate uv with respect to x, then I'm going to have to integrate the other side with respect to x also. When you integrate the derivative of uv, what are you going to get? Just uv. Okay. And then here, I'm going to integrate u prime v with respect to x plus, and I'm going to integrate u v prime with respect to x. All right, now the derivative of u with respect to x, instead of writing it as u prime, which is kind of a shortcut, I can also write it as du dx. And then times v times dx. And then over here, when I took the derivative of v, I took it with respect to x, so v prime could be written as dv dx. So my dx's will cancel, and I'm basically integrating v and du. Plus, and then here the dx's cancel, and the integral of u times dv. And now I'm just going to solve this equation for the integral of u dv. So the integral of u dv equals uv minus the integral of v du. And that's your integration by parts formula. And if you'll look down in the box right below that, that's the formula. But I just kind of wanted to show you where this formula comes from. Now, what this formula means is that what you're going to do is you're integrating a product of two things, but you're going to let one of the factors be your u and one of them be your dv. And from here, or at this point, I just kind of want to jump into showing you some examples and how this works. Okay, so integration by parts. If u and v are functions of x and have continuous derivatives, then the integral of u times dv equals uv minus v du. Now, that seems like a really complicated formula. However, if you think of uv in science, what's uv? Or in terms of the sun, ultraviolet. Okay, so our formula is ultraviolet minus, and this big, the integration symbol kind of reminds me of the Superman symbol. So super in V-do is super voodoo. Yeah, it's a stretch, but, and I don't know, is that how you, is it voodoo, like that? Okay, so the formula is basically ultraviolet minus super voodoo. UV minus the integral of V du. It works, I promise. All right, so this formula expresses the original integral in terms of another integral that's hopefully easier to evaluate. So the hardest part of this is identifying which part of your original integral you're going to let the u be and which one you're going to let the dv be. It's kind of an extension of a u substitution. And there are a couple of general guidelines. Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. So if there's part of something you're trying to integrate that fits an integration rule, you're going to let that be your dv. And then try letting u be the portion of the integrand whose derivative is a simpler function than u. Usually, this is going to be a polynomial function. And with that said, let's just jump into working some of these problems. Okay, so I've just rewritten the formula at the top of the page. So the integral of u dv, what I want to do is I want to let one of my factors be my u and one of them be my v. U is usually, if you have a polynomial or something like an x to a power, you're usually going to let that be u. But you have to make sure that the other part you can easily integrate. So if I were to let u be x, the other part would have to be the dv. And what's left is e to the x dx. Can I easily integrate e to the x dx? Yes. And the reason I have to integrate it is the formula that I'm trying to turn this into has a v in it. So if I let one of the parts be dv, I have to integrate it in order to figure out what v is. Okay, so once you identify your u and your dv, you're going to take the derivative of u. So what's the derivative of u? 1 dx. And then if dv is e to the x, v is going to be just e to the x. And you don't have to put your plus c in yet. We're going to kind of put that in at the end. Okay, so let's just fill in the formula. So uv is going to be x times e to the x, and then minus v du. Well, v is e to the x, and du was dx. And the thing about integration by parts is that you're using an integral to help you solve an integral, but hopefully the new integral is easy. Can we integrate e to the x? Absolutely. So the answer to this problem is x e to the x minus e to the x, and this is where I'm going to put in the c when I do my last integration. Okay, so what we've done is that is the answer to the integral of x e to the x dx. If you were to turn around and take the derivative of this and simplify, then you would get x e to the x. Okay, so our first thing is to identify u and dv. What do you want u to be? X squared, okay. So therefore, dv has to be ln x dx. All right, so I take the derivative of u is 2x dx. And then I have to integrate dv to get v. Well, what's the integral of ln x? The derivative of ln x is 1 over x. I left off my dx right here. Anybody know how to integrate the natural log of x? We've actually never integrated ln x. We do not know a function at this point whose derivative is ln x. So what Tamara is suggesting is scratch this and let's switch our u and our dv. So we're going to let u equal the natural log of x, and therefore dv is x squared dx. Most of the time, if you have x to a power, that's going to be your u. But every once in a while, it's not. And the reason you'll know it's not is because you can't integrate the other function. All right, so what would du be? Yep, dx. And v is going to be 1/3 x cubed. Okay, so we're trying to turn this into uv minus super voodoo. So uv is 1/3 x cubed ln x minus the integral of v is 1/3 x cubed times du is 1 over x dx. Now, 1 over 3 x cubed times 1 over x looks a little bit complicated to integrate right this second, but how could I rewrite it? Yeah, 1/3 x squared. All right, how do I integrate 1/3 x squared? Looking ahead at number 3, there are certain functions that we have taken the derivatives of, but we haven't actually integrated them. Ln x was one of them. Arc sine is another. We've taken the derivative of arc sine, and then whatever that is, we've integrated to get back to arc sine, but we haven't actually integrated arc sine. And that's what it's asking us to do right here. Now, integration by parts is usually used when you have the product of two different functions. However, you can do it with one function because you can let your u be the function. So we're going to let u be arc sine x. So what's left for dv? Just dx. And can I integrate dx? Sure. All right, taking the derivative of u. Here's the $1,000 question for the day. What is the derivative of arc sine? Y'all are good. 1 over the square root of 1 minus x squared dx. And if I integrate dv, I get v, and the integral of dx is x. All right, uv is x arc sine x. Minus the integral of v du. So x over the square root of 1 minus x squared dx. Now, because I had limits of integration on the 0 to 1, I still have limits of integration of 0 to 1 here. And technically, right here, I should put in the, like I'm going to evaluate that from 0 to 1, or you can just wait until the very end. Once we've totally integrated everything, then we can plug in a 1, or plug in a 1 to everything minus plug in the 0. Okay, so x arc sine x, I'm done with that. Now I have to integrate x over the square root of 1 minus x squared. Okay, put the u in for 1 minus x squared. I like that idea. And this is not a u and a dv, it's just a regular u substitution at this point. So therefore, du is negative 2x dx. So I need a negative 2, and therefore a negative 1/2. So now I'm going to have plus 1/2 outside. All right, so I have 1/2 integral of 1 over root u, so u to the negative 1/2 du. Now, normally, right here, I would change my limits of integration. However, I think what I'm going to do is I'm going to, over here on the right side, I'm going to integrate that, and I'm going to put it back in terms of x's and not change my limits of integration, because this x arc sine x here needs to be between 0 and 1, and I'm just going to, I want to keep that all the same with the problem. So integrating u to the negative 1/2 is 2u to the 1/2 times 1/2, so just u to the 1/2, which would be 1 minus x squared to the 1/2. So x arc sine x plus 1 minus x squared to the 1/2. Okay, so plug in our 1. We're going to get arc sine 1 and plus 0. That's nice. Minus, when you plug in your 0, you're going to get 0 plus 1. So arc sine of 1 minus 1. And And what angle has a sine of 1? Pi over 2.